Now here's our first pattern, a difference of squares. We'll explore this pattern by starting with the answer, by starting with the factored form. So essentially by going in the direction we're a little more comfortable with, expanding to binomials. What happens when I multiply x plus 5 times x minus 5? Well, let's carefully FOIL it out. The first two, x times x, give me x squared. The outside two, x times negative 5, gives me negative 5x. The inside two, 5 times x, is positive 5x. And finally, the last two, positive 5 times negative 5, give me negative 25. The two middle terms are like terms, so I get to add them together, and negative 5x plus 5x is 0. So I'm left with x squared minus 25. Before we even explore this relationship further, let's have a look at the second one. You can probably do this one quite quickly. First, x times x is x squared. Outside, x times negative 4 gives me negative 4x. Inside, 4 times x gives me positive 4x. And finally, the last two, positive 4 times negative 4 is negative 16. Once again, the middle two terms are like, and they sum to 0. And we're left with just x squared minus 16. What do all of these have in common? Let's have a look before we start with x squared minus 9 and rewrite that in factored form. Well, for x squared minus 25 and for x squared minus 16, I notice I have a perfect square and a perfect square with a minus sign between them. So subtraction can also be referred to as a difference. So perfect square, minus sign between them is a difference of squares. We had the same pattern here with x squared minus 16. X squared is a perfect square, 16 is a perfect square, and there's a minus sign between them. What does the factored form look like? Those are the binomials we started with. Well, notice that the square root of x squared is x, which is why we have an x in the first spot of the binomials, the first term of the binomials. The square root of 16 is 4, which is why you have 4 in the second term of each binomial. And then if I give one factor a positive plus sign and the other factor a negative sign, I will always set up the situation where the middle two terms cancel. You can try it with any number of factors set up this way. So let's look at this unfactored form, x squared minus 9. I know it's not factored because I have more than one term. What's the square root of x squared? Well, it's x. And the square root of 9 is 3, so they are both perfect squares, and there's a minus sign between them. So this does fit the pattern of a difference of squares, which means I know that the answer will look very similar to these first two questions. So the x goes in the first position, the 3 in the second position. One gets a plus, one gets a minus. And we're done. That's the factored form of x squared minus 9. If you're not sure and you need some convincing, try multiplying that out. X times x is x squared. X times negative 3, negative 3x. 3 times x is positive 3x, and positive 3 times negative 3 is negative 9. Lo and behold, we get x squared minus 9. So once we recognize the pattern, perfect square, minus sign between them, we already know what shape the answer has to take, what form the answer has to take. So the difficult part is sometimes recognizing that we have a difference of squares. Let's look at a couple examples.
So the instructions on this slide just tell us to factor completely. So we have to decide what strategy we're going to use. We need to look at the pattern and see if it fits one of the patterns we're familiar with, which at this point is only a difference of squares. But we also can't forget about common factors. I'll cheat a little bit here and give you a heads up that none of the questions have common factors in this case, but it is the first type of factoring we covered for a reason. It's the most common or most commonly used, and it's the one we're going to do first. We'll explore that a little later. Now let's have a look at these and determine whether they all fit the pattern of a difference of squares. Let's look at the first one, 9x squared minus 1. Is 9x squared a perfect square? Yep, Its square root is 3x. But is 1 a perfect square? Absolutely. The square root of 1 is 1. It's one of the numbers we tend to forget. Is there a minus sign between them? Absolutely. Now notice too that when I'm asking whether the second term is a perfect square, I'm considering the absolute value. I'm considering the negative sign separately from the value. I'm not asking whether -1 is a perfect square. In any case, once we've established that we have a perfect square, or a difference of squares rather, two perfect squares minus sign between them, we know what the answer will look like. We'll put the square root of the first term in the first term of the binomials. The square root of the second term goes in the second term of the binomials. We get a plus in one and a minus in the other. Not sure that they're equal? FOIL out your answer and check. Let's look at this next one. 81y squared minus 4. 81y squared, perfect square. 4, perfect square. Minus sign between them. We have a difference of squares. I know what the answer will look like, so I'll go ahead and draw my brackets out. I'll feed in 9y, the square root of 81 squared, in the first spot, 2 in the second spot, the square root of 4. 1 gets a plus, and 1 gets a minus. Of course, you can write this out left to right if you're comfortable with it, but it's sometimes nice to start with a bit of a pattern and fill it in. Moving along, 36s squared minus 121t squared. The square root of 36 is 6. S squared is, of course, a perfect square. The square root of 121 is 11. Perfect square. And, of course, t squared is a perfect square. So there's more going on in this one, but it fits exactly the same pattern. So once again, we'll give us our boundaries and fill in the square roots. 6s and 11t. 1 gets a plus, 1 gets a minus. If you're not sure about this one because it's a little more involved, this is our final answer, but let's FOIL it out. 6s times 6s is 36s squared. Looking at the outsides, I have 6s minus 11t, so that's minus 66st. The insides are 11t times 6s, so plus 66st. You see right away that our middle terms, the like terms, will disappear. We'll sum to 0. And then finally, 11t times negative 11t is negative 121t squared. So that will work out. Okay, now tackling this last one. Is it a difference of squares? Yes, it is. Big picture, how many terms are there? We're always going to go back to the ideas of factors and terms. It has two terms. X plus 1 all squared is the first term, and 4 is the second term. You might be tempted to expand this out. So you might write x plus 1 all squared is x plus 1 times x plus 1, and then subtract the 4. And we'll see whether or not this works in a moment. But why don't we have a look at the original question as written and decide whether it's a difference of squares first. Is x plus 1 all squared a perfect square? Absolutely. And its square root is x plus 1. So I'll go ahead and tuck that in. I'm assuming we have a difference of squares. 4 is a perfect square. 2 is its square root. Yeah, we have a minus sign between them, so this is absolutely a difference of squares. So we get a plus and a minus. Now this x plus 1 didn't really need brackets. I just threw brackets in to clearly show where it came from. But now I notice that I really didn't need them, and I can simplify inside these brackets quite a bit, simply by removing them and then adding like terms. X plus 1 plus 2 is x plus 3. And x plus 1 minus 2 is x minus 1. That's nice and tidied up, and we're done. Now what if we'd gone ahead and decided to expand x plus 1 times x plus 1? Well, you'll find you get x squared plus 2x plus 1. And of course, we still have a minus 4. And then collecting like terms gives us x squared plus 2x minus 3. Turns out that we can factor that as well. It's a quadratic trinomial. If we factor it, we get exactly the same final answer. We just haven't looked at quadratic trinomials yet, but they are our next topic. So you can factor this in either form. But here, if you recognize it as a difference of squares, we can get to the final answer in 1 or 2 lines. So it's sometimes worth looking for that extra pattern.
Okay, I've given away the answer to this one to some extent in the first sentence. The question asks us to factor completely. It doesn't tell us how to factor. That's up to us to figure out. My hint to you, what's the first pattern I suggested we look for? Common factors. We could have a look at these three questions and treat them the way we did the previous ones, or the ones on the previous slide. Right? We have a binomial with a minus sign in between, and it's possible that this is a difference of squares. A squared is a perfect square, but 5 and 125 aren't. And even if one of them was and the other one wasn't, this is not a difference of squares. So we have to abandon that approach for now. But again, the first kind of factoring we should look for is finding a common factor. 5a squared and 125 are both divisible by 5. So I'll pull out 5, and then I have a squared minus 25 left over. Okay, let's have a look at what's left over. A squared minus 25. That's a familiar pattern. That's a difference of squares. So I'll keep that greatest common factor out front. And inside the binomials, I know what I'm going to have. The square root of a squared is a. So a will be my first term in each binomial. The square root of 25 is 5. 5 will be the second term in each binomial. 1 gets a plus, 1 gets a minus. And that's it. If you take those three factors and multiply them, you will end up with 5a squared minus 125. We know what we get when we multiply a plus 5 times a minus 5. We get a squared minus 125. And when we multiply that whole lot by 5, we're right back at the beginning. So that works. Have a go at 2 minus 72b squared. It's the same situation here. The only thing we can do right now is to pull out a perfect square. Both 2 and 72 are divisible by 2. So I'm left with 1 minus 36b squared. It looks a little bit odd. It's sort of end heavy, but 1 is a perfect square and 36b squared is a perfect square. So I know that I do have a difference of squares, and I'll have 1 plus 6b and 1 minus 6b in my binomials. The last one is a little bit sneaky, but only because there are two different approaches we can take to it. If you follow the pattern I'm trying to establish here, that we should definitely pull out a greatest common factor first. What did we get? Well, 16 and 4 are both divisible by 4. So if I pull out a 4, I have 4 minus x squared remaining. Is 4 minus x squared a difference of squares? Of course it is. Perfect square, minus sign between them. So I have 2 plus x and 2 minus x. And we're done. That is factored completely. But if I go back to the original question, I notice that the way it's written is also a difference of squares. 16 and 4x squared are both perfect squares. So I could have gone ahead and factored it as a difference of squares. Here are my binomials. The square root of 16 is 4. The square root of 4x squared is 2x. One gets a plus, one gets a minus. But the answers don't look the same yet. Okay, that's fair. But we did an extra step here. We pulled out a common factor. What I notice now is that in each of my two brackets, I have a common factor. Right? 4 plus 2x has a common factor of 2, and 4 minus 2x also has a common factor of 2. So I'm going to pull out a 2 from each. What happens when I pull a 2 from 4 plus 2x? I get 2 plus x. When I pull slightly odd looking 2 there, out of 4 minus 2x, I get 2 minus x. So all I've got here is 2 times 2 plus x times 2 times 2 minus x. Why don't I take those 2's and pull them out front? 2 times 2 is 4. That tidies it up quite a lot. And now we have the same answer as we had before. You can go in either direction. You can choose to treat it as a difference of squares first and then pull out common factors if you have them, or you can pull out the common factor first. Generally, if we pull out a common factor first, our problems will be easier to tackle. This is also true for the triangle.